Morning, everybody. David Shapiro here. Today we are going to go over microservices. So I've posted a question on my YouTube channel asking if people wanted to learn about microservices because I realized this is something I've been going on about lately, and everyone has been here for GPT-3, and you might not know what a microservice is. So without further ado, here we go. What the fuck is a microservice? I don't care about getting demonetized. And why is Dave obsessed with them? The short version of a microservice is that it's when you break software into independent chunks. So the old school way of building software was that you'd have a monolithic application where all the software is put together in the same executable file or in the same server, and so on. And this works up to a certain point, but as you can imagine, once you get bigger, it's really difficult to run. And so then what you do is you break all the parts of that software down into smaller chunks, and then you have them communicate with each other like independent units or teams. So monolithic versus microservices. There is a few steps in between, but this is where we started and this is where we're at. Okay, but why? The primary reason is that microservices are easier to build and maintain. It's a simpler architecture. So rather than have one big thing that has all these internal parts that have to communicate and be fine-tuned, and if one part breaks, it can make something over here break. By decoupling all that, it is a simpler architecture. It's more like a web. And also, if one component is faulting, you can take that component out, fix it, look at the communication that it has with other components, and you can see exactly where in the network you have problems. Another principle of microservices architecture is that it's loosely coupled, meaning that if this service blows up because its database blows up, the rest of the application might be okay. Another key advantage of microservices is that you as one human cannot understand the entirety of a huge platform like Amazon. You can, however, understand one microservice, or actually several microservices. Generally speaking, a Scrum team will be responsible for 3 to 7 microservices. And so you have these smaller components that one human or one team is able to fully understand and master, whereas you cannot have that in a super huge monolithic thing. Another thing is that it is much more dynamic and flexible and can evolve over time, which in today's world where Amazon and Netflix and Facebook and whoever else are always adding new services and features, that flexibility is critical when you adopt a microservices architecture. Okay, a little bit of background: who, when, where. So microservices architecture was pioneered by Amazon in a big way. They didn't invent it, but once the Amazon platform got too big, circa 2005, I think, they started breaking it down into smaller components. So really, it was a matter of necessity. They said, this is unmanageable. We need something more modular. Now everyone uses it. Pretty much, if you're doing software development today, it's going to be in microservices. Like there's stuff on AWS and Azure and stuff that allows you to just run code and containers and stuff, and so everything is containerized. You even have serverless code where you just send a piece of code to the cloud, it executes the code and sends back the result. So you don't even need a container. So we're getting even more distributed. It's like nano services. Microservices really took off around 2010. That's when AWS services really started becoming popular, although, again, they were available before that. Some of the key benefits: you can use any language. So say, for instance, you have one team that's writing a microservice in C because it has to be fast and efficient and cut down. So, for instance, a machine learning microservice might be written in C. Whereas you might have a web front end that's written in like React or something else, right? What is it? My brain isn't giving me. I haven't done any web. I'm not a web developer, and it's been a long time since I've worked with web developers. Anyways, point being, you can have different microservices that have different functions, and you can use whatever language or technology stack is ideal for that particular function. But then they communicate with a standardized communication thing, such as, excuse me, a REST API or an AMQP message broker. You don't need to know what those are specifically. Just know that those are two primary ways that different computer or software components can talk to each other. So rather than everything being encapsulated, it says, hey, I'm going to talk to you. What's your phone number? Basically. It allows for continuous delivery. So Amazon never goes down, right? You might lose one or two functions, but it's always adding stuff and it's just bolting on new parts. And so that idea of bolting on new parts as you go, which you can't do with your car, by the way, it takes a lot of work. But that is how continuous delivery works. It's modular, it's scalable, distributed development. That's what I was talking about in the last slide. One principle that I've adopted, and this comes from Unix world, which is every tool should do one thing and do it well. So rather than have a big giant platform that, you know, is like okay and this part's okay and this part's okay, with a microservice, that what you should do is focus on doing that one task and do it perfectly. Okay, so now you know what a microservice is in general. So let's talk about artificial cognition and microservices. Here is a basic diagram of the brain. Sorry, it's not in English. I wanted to make sure that I stuck with Creative Commons licensed images, and this was the best one because it was that I could find because it was simple and color coded. But the point being is that you can see that there are roughly 12 or so, a dozen or so specific big regions of the brain. Each of these regions has much smaller parts that have specialized purposes. There's also different components that are not represented here. So point being is this is the brain. It's got a lot of specialized region. So here's like the brainstem that comes up, and then the first thing is the primitive reptile brain, then the mammalian midbrain, and then the human neocortex, which is the big part on top. So it's like a stack, right? And then off to the side, you've got the cerebellum, which helps control. I think that's a cerebellum. I might be wrong. I should know this. I've read a lot of neuroscience. Thing is I read the parts and then I don't look at the diagram. And so anyways, this helps coordinate complex motions. So for instance, if you have damage to the cerebellum or degenerative disease, your motions will be more jerky and you'll have less fine motor control. Chronic alcoholism will actually shrink the cerebellum, as will any number of other things. Okay, so you get the idea that the brain has specialized structures and regions. Okay, the human brain has 12 main components and hundreds of subcomponents, all with different specializations. That's what I was just saying. Excuse me, I don't know why I'm stuffy. Okay, so what brain disease and injury tells us? The first thing is that the brain is not monolithic. Your brain can break in specific ways and you lose very specific functions rather than global loss. So for instance, if you get a lesion on one part of your brain, it's not like you're 5% less overall. You will have loss of function wherever that brain lesion is. Or if you get like a head injury from a car accident or whatever. So there's a few examples. Acute amnesia, where that has to do with injuries to the hippocampus, I believe. So the hippocampus is this guy right here, I believe. Hippocampus literally means seahorse, and so it's the seahorse-shaped part of the brain. So acute amnesia means you lose your episodic recall, you lose the story of your life, but you don't lose declarative recall. You still remember facts. You still remember how to speak, right? So you can lose a very specific part of your memory, but not even all of your memory. Loss of speech and stroke. So one thing that often happens when people have a stroke is that, you know, you might end up paralyzed on one side of your body. You might end up without speech or any number of things. But that's because a stroke happens and it damages one part of your brain. Loss of motor function and degenerative disease. And then one of the more interesting things is visual neglect and prosopagnosia. So visual neglect is where you don't notice things on one side of your field of vision, or you don't notice specific things because you can no longer identify them. And then prosopagnosia is face blindness, where you see a face and it does not connect to identity recognition. You say, okay, I see a face, I don't know who that is, right? And it doesn't matter if you've seen them every day of your life, you don't recognize the face because the visual visual information of that face does not connect to the episodic recall or the whatever parts of your brain identify that as a person that I know. So there's communication between specialized regions. And damage to those specialized regions resembles a microservices architecture. So, for instance, like if you're on Netflix or Amazon, like, you might get a pop-up that says like, oh, hey, your queue isn't available right now, but all this other stuff is still working, right? That's what I mean by like, you can lose one part, but the rest of it's still working. So all of this interconnectedness in the brain, but also the brain regions can function quasi-independently. So for instance, if you have prosopagnosia, face blindness, you can still see, but you can't recognize faces or specific. There's other kinds of things where like you can't recognize an object. I can't remember what it's called, but there was I was reading about a specific thing where it's like people have lost the ability to recognize specific objects and like they can describe it, but they're like, I don't know what that is. I don't know what it's for. But then they take their eyes off of it and they can still use it because the functional part of their brain that says, I know how to use this tool because I don't need to look at nail clippers to use them. I can feel it. And so they feel it and they're like, oh, I know what that is. I know how to use it. And even if they don't consciously know how to use it, it's weird. You read V.S. Ramachandran, he's got all kinds of stories like that. So when you see how granular and modular the human brain is, you realize, that sounds a lot like a microservices architecture. At least that's what I did. I'm a systems engineer professionally. So I want to tease my audience. Is this a microservice network or a brain map? I'm not going to tell you. I'm just going to say, do you think that this is a map of communications between microservices, or is this a map of a brain or a brain region or what? So I'll let you guys figure it out. Tell me in the comments if you know what this is. Don't spoil it for anyone else. Okay, so how do we copy the brain? Obviously, the human brain is our best model for intelligence, and so a lot of work is put into modeling the human brain as a way to get machine intelligence. All the biggest things right now are deep learning neural networks, right? So it's no surprise to me that our smartest machines, or at least the ones that are most similar to human intelligence, are neural networks. So we're copying the way that the human brain works at a microscopic level, right? But what about the macroscopic level? How about the whole brain, right? Because you can train a virtual neural network or an artificial neural network that has the equivalent of like 1,000 neurons, or let's see, GPT-3 has 175 billion, and it's roughly 1,000 per. So GPT-3 has 175 billion parameters, but it takes roughly 1,000 parameters to model one human neuron. So that means GPT-3 is the equivalent of about 175 million neurons. And the human brain has like 90 billion. So we're still a few orders of magnitude off. Excuse me. So we've got there's two primary ways to model the brain. There's the structural model, which is where you copy the regions and connectivity of the brain. So basically you're copying the organic structure. And this is what you might have heard called whole brain simulation. So I think it was IBM, was working on the connectome, where it was modeling the connectivity of like the entire brain. Because that's the structural model of saying, hey, let's go and just copy this, but in virtual. I don't think that that's necessarily the best way to go. So the other model is the functional model. So the functional model is where you identify discrete functions of the brain, such as memory, learning, visual processing, morality, whatever. You say, okay, let's treat morality as its own function, and then let's copy that. And then you wire it all together like a software application, specifically like a microservices application. I take the functional model approach. It is prohibitively expensive and difficult to map the entire brain and then to run a whole brain simulation. I also don't know that it's ethical, because here's the thing: if you put a brain in a jar and then you turn it on, Like, it's not going to have any sensory input unless you fabricate sensory input, and it's not going to have any sensory output unless you give it, like a virtual body. And what if that brain is sitting there panicking because it's like, I don't have a body, I don't know how to breathe, right? They actually explored this in Caprica. So Caprica was a show that was like a prequel to Battlestar Galactica, and one of the guys, like his daughter died in a terrorist attack, and so then I think it was Caprica, he recreated her virtually, but he forgot to give her virtual like body sensations, so like she couldn't breathe and she couldn't feel her heartbeat, and she's like, what's wrong with me? Why am I like this? And that was a perfect example of why I think that whole brain simulation is probably super unethical. It was just a fictional example, but still. Okay, so we've got the structural model, functional model. I prefer the functional model because like we don't have to reconstruct a brain with 400 million or 3.5 billion years of evolution. We can just design something from the ground up that's better. Okay, so microservices architecture of the brain, like how would we do this? What are some of the domains? So some of the functional domains that you can think about are input. So we've got sensations, but for a machine, you have the possibility of other kinds of input other than the senses that we have, right? So we evolved, the two primary ways we take in information are sight and sound. Vast majority of the data we take in, the information is through those senses. But a machine can have APIs. It can talk to the web. It can talk directly to other machines. So you can have microservices that handle input and sensations. You have output, right, which is actions controlling peripheral devices, speaking, robotic arms, that sort of thing. Then you can have executive functions. So this is where we still model the functional aspect of the human brain. So the human brain has the basal ganglia, which is responsible for task selection and task switching. And so this is when someone says like executive function, this is kind of the fundamental part of what they're talking about. Now, damage to the prefrontal cortex can also impair executive function, but in terms of like what you're behaviorally doing, right? Like if you're listening to someone and you decide to interrupt them, that is if you interrupt someone inappropriately, that is a failure of the prefrontal cortex, because the prefrontal cortex is responsible for self-censorship so that you can behave in polite society. But then the actual task of speaking goes out through the basal ganglia, where it says, I'm going to select this task or I'm going to switch to a new task. I'm summarizing. If you're a neuroscientist, I probably got some of this wrong, but in general, this is good enough for understanding where we're going from here. Other things are like planning and strategizing. We can think very far into the future. In fact, human time horizon of thought is many orders of magnitude above most other animals, with very few exceptions. I think elephants and some birds can think pretty far ahead. But in some cases, it's like, okay, is that instinct? Like, are they actually planning? But elephants can, as a herd, kind of collectively decide like where to go. Say for instance, there's a drought, they can remember like, okay, we got to get back to where there's water, and we know that there's water, 160 miles in that direction. Granted, elephants can also travel like 40 miles a day, so that's only 4 days out ahead. Humans, however, we can think years, decades, centuries into the future. Just having that mental concept of that temporal scale is completely unique to humans. We can also anticipate and predict. Now, the ability to anticipate and predict things is not unique to humans. However, the kinds of things that we can anticipate and predict are. So, for instance, we can anticipate or predict, if you like, say for instance, you learn well enough, you can look at a weather map and you can predict, the weather a week in advance. Animals can't do that. We can also anticipate or predict how humans are going to react, right? Because humans are complex agents, and so the more you know someone, or the more that you're familiar with human thought and human behavior, you can say, okay, if I do X to this person, I'm going to get Y response. So that's what I mean by anticipating and predicting. And then there's morality and ethics. This is obviously a big thing for AGI, or artificial intelligence, especially if we assume that machines are going to become smarter than us one day. And and we assume that we will lose control of them. So I know that many people think, oh, well, they're just all, just give it an off switch. We must assume that we will lose access to the off switch one day. It's just, you build something that's smarter than you, it will outthink you, it will outpace you. That is just kind of an inevitability. And so, yes, that sounds scary, but I'm not worried about it, because this is my jam. This is what I focus on, is making sure that we have benevolent machines that aren't going to kill us or do other unwanted things. Okay, so why take these functional domains and do it as microservices? We can update the machine as we go. It can be a plug-and-play architecture, just like Facebook, Amazon, Netflix are, so that the machine can keep going. You can improve microservices individually, but you can also make sure that those microservices are super robust, that they're not going to fail. And again, you can add and remove microservices arbitrarily. Again, that is that plug-and-play architecture. So Maragi. Maragi is something that I have worked on, and I am now revisiting now that I have a strong enough understanding of both neuroscience and how to model all of this. So this is what my most recent videos have been about, is creating those microservices to create a fully fledged, autonomous artificial cognitive entity. So Maragi means microservices architecture for robotics and artificial general intelligence. Okay, so that's why I'm obsessed with microservices, is because I see microservices as treating the brain like a system rather than a monolith. Maragi, I invented it in July 2018. I went and found my original diagrams. So it is 4 years old this month. It was originally, some of the original experiments I did were with AMQP, which is Advanced Message Queue Protocol. It is a way to have computer components talk to each other very fast. And then I also experimented with REST. I've settled on REST because it doesn't require a broker. So AMQP requires a broker, but REST allows things to talk directly with each other. It was also originally multimodal, where I would have like one service that would like take pictures and send pictures, and then another that would take audio clips and send audio clips. I've done away with that since I wrote Natural Language Cognitive Architecture. I realized that once you get into the core thought module of a brain of an artificial cognitive entity, that you should have one modality, and I chose natural language because it is interpretable and transparent. I did not have the nexus figured out, I did not have the core objective functions, and I did not have cognitive control figured out. So there was a lot of problems when I first came up with Maragi, and all of them have been solved. So here's some of the original diagrams. So this logo is what I made. I knew intuitively that there was going to be some kind of central core. I had no idea what that was going to be. I thought that it would be a database of some kind, something that would organize it, but now I realize there's a little bit more. Here you see a diagram that it's more distributed, and there's kind of no structure where every component talks to every other component. It's much more organized than that today, and I'll show you the latest diagram of Maragi in a second. But these are both circa July 2018 when I first came up with the idea. Let's see. So this is Maragi today, and I've shown some diagrams of this. So we've got the nexus, which you'll notice there's some similarities, right? So there's something in the center that everything orbits around, and in this case it's the nexus. And then there is some cross communication with the other things, but primarily everything communicates via the nexus. So you've got a hub and spoke model of artificial cognition today. And so this is a functional model. This is also a thought first model. So the nexus houses the stream of consciousness for this machine. And so you could basically say that the nexus is the conscious component, although that's not necessarily, that's going to be a misnomer, because people, I can already hear people saying, like, you're building a conscious machine. It is functionally conscious, not phenomenally conscious, not philosophically conscious. It's just, it's meant to model or emulate the human stream of consciousness, and then all these other services would be the unconscious mind or whatever. Let's see. And then, oh, that's it. Okay, so this is Maragi today. Now you're up to speed on microservices and Maragi and what I'm doing and why. So thanks for watching. Like and subscribe, and consider supporting me on Patreon. And that's that.